Okay.
Okay. Yeah. Well.
Perfect.
Yeah. Hello, welcome everyone. So today we have another theory with Vasu speaking about his master thesis. So please.
Yeah, so I'll talk about matrix model and JT and relation between them. First, I will start with matrix model. So, what are matrix models? They are zero-dimensional quantum field theory. The specific case that we will consider is Hermitian matrix models with UN symmetry. And for that, the action is given by this. I have bad handwriting, so please ask what I will ask if you are confused. This is the entire action, not just argue. So, yeah, there are a lot of new things here. First is that this, these are the terms, these are the matrix fields involved. And since it's Hermitian and has even symmetry, it has like it's an n cross n matrix, so but it has n independent quantities in it, and these are the like coupling constants. And for in general matrix models, you can have any number of terms here. You can even go to infinity; it's not a problem. But yeah, so this is the general action for matrix model. So
Can I ask?
Yeah.
Is this so? You said it's zero-dimensional.
So it's also the Lagrangian, yeah.
Yeah. So that's not integral over
No,
everything.
nothing.
Yeah.
Yeah, there are many like yeah. So if you want to have some like add some time dependent potential or something like that, all you can do is they say add another potential on matrix with some like parameter p that you can vary. It's not strictly time because it's zero dimensional, but you can do something like that. Yeah, I'll talk a bit about it later. So yeah. So for this, the partition function is given by since it's even gate theory, you have to divide by the volume of given group. And this is the measure for the integral. And yeah, so this is where things start getting confusing because, okay, so in normal QFT, this kind of integral just has a couple of fields in it. But that's not the case here. Here we have the n independent quantity. So like this is not just a simple field anymore. Like here, for example, in matrix models, dm is given by something called a R measure. So it's see real part, MRJ, and investment part of MRJ. Yeah, so this is the measure for partition function. Well, you might think, okay, this makes it complicated, but you can, in general, right, if you have some trace for n square, you can just, in general, you can write it as mii squared, as real part of mij multiplied by plus imaginary part of mij, all of them squared individually. So
you need another equality sign.
yeah, here, yeah, sorry, yeah, it should be, yeah, there's no one. So yeah, this is the measure, and like for if you just take this term, this is just mii squared plus real part of mij squared plus imaginary part of mij squared. So for simple cases, this just using this measure, it actually just give you a Gaussian term because we have square with exponential and measure here. So that's why if you just take this part, it's called a Gaussian matrix model. So, okay, now that we have an action, we have partition function, the main thing we want to know is, okay, what does a correlator look like? So for any like some n, I'm just writing it heuristically now, or that I explain in detail later. If you have something like some m I j to m k l, it'll go something like yeah, it looks something like this multiplied by the relevant coupling constant. So this is what normal coordinates looks like. So as you can see, you can't just simply write a single line for finding the diagram and say, okay, this is denotes everything. Because for now, okay, this seems fine, but if you have something more complicated, it's not going to generally be sticking to this 2D. You can have an arbitrary, this can become some sort of 3D diagram. For example, you can have something like this. If you have something like this, okay, this is really not 2D, but in 5-dimensional diagrams, in regular 5-dimensional diagrams, this will have the same just going on. So that's why we use something called paragraphs, because it's fat. So the paragraph notation, like, it probably gives you the way to characterize your diagrams geometrically. So when you do something like that, what you're essentially saying is, okay, so if you are able to distinguish geometries of diagram based on this, maybe you can look at some properties and order them by something. I mean, for now, we don't know, but it's an instinct. So what we can say is, okay, so what can we order it by? So we have n here. In our matrix world, we generally take n to be large, so we can try to order it by n. So in general, here you have, since this the number of these are called colors, like a QCD, so the number of colors for something like this will go as n. So I mean, for a general diagram, this will go as n. So for complicated diagram, multiple versions of propagators will go something like this. Now, okay, so
So I, J, K, L each goes from 1 to n.
no, these are in matrix indices.
So it's an n cross n matrix.
Yeah.
So it goes
I
from.
mean, like, this is okay. This is not a matrix multiplication. It's like Mij going to Mkl. So I mean,
I think I'm talking about the. Okay, yeah, it goes from 1 to n.
yeah, I mean, it goes from 1 to n in the sense that like what these are just delta functions.
Yeah.
So yeah, it does go from 1 to n, but like, this is not naively n squared.
Yeah, that is the question.
Yeah.
So it's not n squared.
No, it's not. Wait.
No, because I can go to L, N, L. So you have n, right? N of these. So J to K, so you have n of these. Is it n squared? I don't know.
Yeah, so the thing, yeah, okay. Yeah, so this is something you're heuristically assuming, so but we still haven't taken into account how the these coefficients come up and what they are. So in general, what we do is we don't take n to large n directly. What we say is, okay, we have something called a tooth coupling, and we set this to be constant so that when we take large n, this becomes very small. So when we do counting like that, it doesn't go to n squared. Okay. I mean, yeah, so yeah. But if you don't do that, then purely just talking with the taking GS to be constant, then yeah, you might get n squared, you'll get n squared. But if you do if you use two coupling, yeah, it won't. Yeah, so yeah. I've given a heuristic picture. Now I'll talk about what the specific case of Gaussian matrix model because one, it's easier, and two, all we have done is given a hand-daily explanation. We want something concrete. So, okay, for Gaussian matrix model, you have for now, we do not worry too much about this. One has already been calculated in literature, and two, in most cases, like calculating correlators, it doesn't come into too much. So,
Yeah, it's just a concept.
yeah,
That depends on it.
yeah. So this is the partition function, and okay, so another thing that we want to do is we want to find out the expectation value of some function of all these matrices. If we want to find out something like this, because at the end of the day, when you calculate all the primary diagrams, everything, you have some function of m inside, and you want a reliable way in which you can calculate this. For me, if you have in general, if you want to do a propagator like this in matrix mode, you can see that okay, you can just take a derivative with respect to GS and you demote this here and you can do it. But okay, what if you want to do something of higher powers or higher orders, then you do not have general way to do it. The thing is, in matrix mode, we can try to derive a way in which we can do all of that. Like I said before, matrix model has only n independent parameters. So what we generally try to do is we try to diagonalize this and do it using something called we try to get it in terms of eigenvalues. So there are other ways to solve it, but we will first start trying to do it with eigenvalues. So this is yeah, you might have noticed the two coming out. It's just like sometimes you have two, sometimes you don't. I mean, this is a different thing. It's not the same as that one. Yeah. Okay.
Okay, so that factor two is just convention, or is it?
I mean, everybody uses like
It's just convention. I mean, you're not talking about something convention different, right?
no, it's just another convention. Yeah, I don't know why, but like everybody who publishes a paper on matrix model uses their own convention. So yeah, so yeah, what I'm doing is like yeah, this is the kind of reform. Okay, so before I go further, I'll say something. Yeah, so W and something I introduced into called omegas and GS, their meanings will change from time to time. So like whenever I start writing from scratch, it just like it means I'm following some other prescription. So yeah, trying to clear your head. It's generally there are a lot of variables, so we try to stick to the few that we have. Okay, 1 second. Yeah. So yeah, if we have something like this, what do? You might think, okay, for example, I'll give you a pictorial example of what this is. So first, you have, let's say you have something like this. So what this means is that there are two sources with 3 legs, and you're trying to find out the diagram. You're trying to find out connected diagrams between those two in Gaussian matrix model. These are the kind of things that I'm talking about. In general, it's not very easy to make. Like for this case, it is possible if you rigorously, it is possible to just keep taking derivatives and use delta functions to get your theory. But if you go for much more complicated diagrams, which you will do, then it's not very easy to just keep taking derivatives, trying to demote from the exponential and trying to find out how these function. So yeah, I'll try to, okay, what these are is something like this. You have two sources like this. So you try to find out connected portions of these. Now, I'll use this to demonstrate something fundamentally different about matrix forms. That like why we have to use star graphs and why like n ordering actually helps is that okay, there are three unique diagrams that you can get from two correlators of this sort. One is kind of easy to see. It's just it's just all the three legs are connected to something in the other part of all three legs. This is a pretty straightforward diagram. The other is another pretty straightforward diagram.
So the fat sunset and the fat downhill.
Yeah. Yeah. So, yeah, these are pretty straightforward. And even in final locations, these will appear pretty much the same.
So these are both representing the previous one that you drawn.
No, these are this, the possible diagrams of this.
Okay.
These are two tetragonal vertices,
Yeah,
and you're just trying to do final diagrams.
yeah. So there is one more, which is pretty unique in that it goes something like this. Yeah, it's yeah, so it's like this. These are all cross-connected. So yeah, when I said these go by the color span, we can see there are three colors here, there are three colors here, and there's only one color here. You can trace them around, and there's just only one edge here. Now, when we calculate what are the contributions from these diagrams, we can do that. So, like this. The contribution to this is this one. Okay, so I can go the explain. So there are there are well three different ways you can connect one and then the other two automatically falls in place. In this case, it's 9. Excuse. It is 9 because once you connect this, you can either connect it to the opposite side and get another dumbbell, or this side and get another dumbbell. So there are 9 possibilities. And here, there are 3 possibilities, but since there's only one color, you will get a diagram like this. And here you can see the first appearance of organ here. Except these two diagrams, this diagram is n squared suppressed, and this one is clearly not linear. So that's one of the big advantages in matrix model is that all non-planar diagrams are at least n squared suppressed. Yeah.
Are there not more non-planar?
Yeah, I mean, these are cross-wired. So
Yeah, are there not more non-planar diagrams? I would imagine that if you only have here, you have 3 cross-connected.
Here, in this specific case, here, there's only one non-planar option. And you can go for higher vertices in higher options.
But couldn't I make twists on the other 2 seconds?
Here.
Yeah, there. Not that's topological, not interesting. But what about if I make it twist?
Here.
Yeah.
Here.
Yeah.
The first one. Yeah, one second.
What is the interaction term here? So it's just no interaction terms with just the kinetic term.
That's the thing. There are see when you say kinetic term, you have something with derivatives usually. There are no derivatives possible here.
No, but
This is the interaction term. The entire action is the interaction term. There are no kinetic terms. Generally, in matrix models, we call these potentials. It's just, that's all there is. There's no propagation, there's no. It's just,
So, but it is a cubic interaction, right?
yeah.
No, but if it's a cubic interaction, he needs to turn on the G3.
You can just take an extra propagation value.
That's the problem.
No, if he doesn't turn on the G3, then it's not a cubic interaction. Like,
Oh, okay, but it is, he's
Okay, so-
basically, what's called the, is doing the free,
three things.
No, so, yeah, what do you?
I mean,
But
it's
the
the free
expectation value of him.
expectation.
The vertex is coming from that.
Yes, but what I was saying is, if you have.
Yeah. Thing is, what you do is that you bring this on 3 times, and then you like take out the delta function such that you will have diagrams like this. I mean, these are only possible ways in which you can take out the delta
So
function.
from each vertex, how many lines are coming?
3. You just don't need to have a. I mean, that's the thing. It's not the odd.
I mean, fat tree, with fat lines.
But shouldn't you need a I mean, the G3 for it? Like,
No.
if you look at WM.
Yeah, it's just differently bringing it downstairs and then you turn off the interaction upstairs.
Okay.
I mean, you don't even have to do that. You can just bring this down to 3 times.
Yeah.
And then what you do is you just keep switching the indices until you have like one vertex with just 3 legs. That's why you can only do like even power of trace and cube. You can't do odd powers. Because you don't have a cubic term. You can directly get this from that. I mean, like, that's the thing. When you say you have cubic or quadratic, you usually have. I mean, you bring something down, but you have these constraints of, well, you do not have a kinetic term, you just have a potential, so we can just keep bringing potential down, and then you just keep making up whatever kind of vertex you want. It doesn't really matter that you not have a cubic term in the potential. As long as you're able to have this 6 power term, we can just bring this down 3 times, keep switching the indices until you get these diagrams. Until you get diagrams such a way that this one vertex has 3 legs.
Yeah, I mean, whatever you want to, way you want to do it, but I mean, yeah, sure.
Yeah.
But, okay, so how's the counting? So you get 3 and 9, 3, how did you get that?
So yeah, you have this.
Yeah.
So like you have 2 of these. You say you connect this one to this one to get this. Like, there are 3 ways to connect this to anything here, but then the next one will be fixed. Similarly, for that, you connect these 2, but then if you connect this, you can do another double here. You can then connect this one to this one, then connect another here double, but the double will come all the board and in the board, but it will still be there. So there are 9 possibilities for that. Yeah, so okay, it's perhaps good if I write down what these look like. So this, if I do the calculation, it's completely, but I'll just give you one for any of this. Okay, I'll do this. So this. So you see, you don't need a G3 term. These are just G2 terms. But when you rearrange the indices in a way that like you can connect like these 2 and so on, you can these correlators are just they are still 2 correlators, but they are also connected to other parts. So yeah, you don't really that's the thing about it's quite it's not the normal way in which in QFP you just bring down a single potential and it gives you a single vertex that just has 4 possible legs. You can just like,
You could call it strict interaction vertex.
okay.
Strict from the field. Fields are strict.
Oh, okay.
There's only delta functions left, right?
Yeah. So, yeah.
You don't have to erase, you can use the other thing.
Oh, okay. Yeah. Well. Yes. We'll go back to our main problem. It's just that if you have some FM like that, how do you calculate it for? And yeah, the thing is that FM is gauge gradient. Why do we come to that? So what we do is that at first we'll just diagonalize M. It's just now completed with diagonals. And we say, well, choosing diagonal is just choosing the gauge, so it's not gauge fixed. So what we can do is that once we just choose this as a fixed gauge, and we also have to take care of the we just have to explicitly state this gauge form, the gauge fixing. So what we do is that we say we introduce a term. And this like what it's using, so it just means that you have an use. Like we just have to introduce a term like this so that the gauge is automatically fixed. But yeah, the problem comes to the fact that like already for simple measure, you have something so complicated. Even the first order term will have many terms if you try to calculate individually. If you have a delta function like this, it's like even at the basic order start becoming a nightmare. So what you do is that you try to, okay, let's say this can be written like instead of that, I'll write something like this. I'll define something new. I don't know what this is, but I'll just introduce it here.
I think this is called the effect for
Yeah, it is a level of fifth one. Yeah, it has quite a many words for so it's yeah. We use other form of fixing, but here we don't know what the explicit form of this is. So here we just introduce it. So here it is just yeah, we'll have something like this. Now, what we can do is that first thing is to do is that like this can be separated again now, because now that we have chosen that again, FFM is already gained median, none of this depends on what's going on here. And another thing is that from now on, we will switch to writing the unless I explicitly say otherwise, we will switch from M to its eigenvalues. So how does the switch go? We now write it like this. This is the contribution from this. Yeah, we have written everything down in terms of the eigenvalues of the matrix in the form. So now, so in literature, people have made some calculations and found out that for in general matrix model, what we do is that at first we know how we can calculate for Gaussian matrix for what Z is. So like to do that, it's just I don't have that. So yeah, you can calculate for okay, I'll just see how much I have. So if I have
You should go over the time. It's like not by 1 hour extra, then.
Yeah, if I start doing that, I'm going to be too long. So, yeah, so what, okay, I'll just slowly explain what we do. So what we do is that we don't know how to calculate this because it's something new. But we do know, like, if I just remove this term, this rest of the term is just Z. And we can calculate Z for the very basic Gaussian matrix model in a straightforward fashion. So what we do is that we do that calculation, and we also try to find out what people have found out what volume of human group is, and we see that what we do, we compare that to this part, and then we reverse calculate what it is, in reverse engineer what it is. So people have done that and found out this term is something called van der Waals determinant square, and it's given like this. Yeah, I mean, like I'm also skipping free energy. So if anybody hasn't done this thing, let me know. I'll tell you after the thing.
So what did you say it was called?
It's called van der Waals determinant square. So yeah, this is what the nature of this. The square is. So with that, we will now have a better way to calculate what XFM is. Now all we have to do is that input all the complicated functions of the matrix model in terms of its eigenvalue and have this attached here, and then we just perform the straightforward integral. So I have to write what F is in terms of eigenvalues. It's given by yeah, this is the partition function in terms of in eigenvalue restriction. Now, there is actually, I didn't explicitly say, but there is another way in which you can solve matrix models called modifying the variable. What you do is you just try to shift the matrix model so that you complete the Gaussian and try to find out the solution. That is how we calculate the partition function for Gaussian matrix model. But that's not easy when you have higher more complicated series. For simple ones, yes, there are there are actually two methods, but the eigenvalue restriction is the one that actually works best when you try to do very complicated systems. So yeah, now that we have this, we need to solve this. This is not, this is very absurd. So there are two primary methods to solve this. So one is called the saddle point analysis, where we extremize the action and then find what we minimize and then go forward doing that. The other and more explicit method of calculation is called orthogonal polynomials. And what we try to do is that try to write this combination as a product of orthogonal polynomials. So when we try to do that, then we will be able to get partition functions as just some. What we have seen in other quantum mechanical models. You just have two orthogonal polynomials describing the system, then you have one state will be described by one set, the other will be the other. There will be others, two orthogonal polynomials describing the set, and then you can do all of that. But the problem there is, okay, if you have some specific potential, maybe by some guesswork, you will be able to find the orthogonal polynomials, in which case all of them are directly solvable. Or it's your guesswork is as good as the best way to obtain solution there. If you don't know what the answer is, you can't do anything. So we'll go with the saddle point analysis. So here, what we do is that we reframe this and say Okay, instead of this, I'll remove this, and I also promote this to the action part. Instead, I'll write something like this. It's called the effective action, and I'll have an n squared there, and that'll be 1 by n squared term added to the terms inside. So what S effective is uh, yeah, so I'm pretty sure I won't be able to do JDW this time, so I'd rather not rush with the simulations model properly. So, yeah. Something you need to note here is that you have the 2D maximum dependent potential here. We didn't do anything explicitly to obtain it, all we tried to do was solve it. But yeah, if you think, okay, these eigenvalues in the two-dimensional space, you already have a maximum dependent potential. So yeah, what we do now is that we can, this is the effective action, then since this is zero dimensional, in order to, like, there is no Lagrange change, so all the equations of motion will be directly done with the action, and you will extremize it, and then see that you can write. I think the proof coupling here. This is just, okay, instead of lambda, just use t there.
And shouldn't there be one more new lambda chain put up there?
Where it is,
You know, in the zip, yeah,
one more,
the lambda, don't take into it the result, lambda J.
no, I mean, this is the diagonal matrix, these are all like eigenvalues of diagonal matrix, so it just be lambda one, lambda two, lambda three, one, lambda, that's it. I mean, yeah, if you do something like that, that's not like a gauge space thing, that's why you have to have one of you and one thing. But this is a fixed gauge where the matrix is completely diagonal, so you only have n terms here. Yeah. So yeah, if you do this, if you estimate the action and try to find out what this is given by all of this here. Yeah. You'll find out something like this. So since we have already taken,
Sorry, this is the equations of motion for the section.
no, yeah. For specific and I will just take the derivative and then, yeah.
Okay.
Yeah, so now what we do is that, okay, since we have already taken larger limit, like this just begs to be converted to something continuous limit. So what we'll do is we'll introduce something called, we'll introduce something here. Like this. And then now we can write it as an integral. This is just
It's a density of eigenvalues.
Hmm?
So it's a density of eigenvalues.
Yes. Here, so, yeah. Yeah, here this is called Cauchy principal value integral. So what it is that if you have an integral that's not very well defined at a specific point, that's defined everywhere, what this type of integral does is this is basically saying like if you have something like but z f of z is not very well defined in C, what you do is yeah. If f of z is not very well defined in some specific point, you just write it as something called a Cauchy principal value integral, and all it denotes is this.
Can I ask one more?
Yeah.
So this equation, the equation of polarization. So you're using a generic W or is it the one that you start?
No, it's yeah, it's a generic value.
Okay. So it's an equation for the W.
Yeah.
Okay.
Okay, so yeah, I might W also be used somewhere else later. So for now, this is the potential. I'll switch to B, then I have another W. Yeah. So, okay, now I have something like this. So well and good, but still I haven't solved anything. I just like rewrote a bunch of stuff. And in order to solve something like this, we will need to introduce some quantity called the resolvent. So what is resolvent? It's defined like this. In omega. Right? Okay, P is just some other point in the plane. I is the identity matrix, and M is also the matrix here. So yeah, going forward, I will not write P into I minus M, I'll just write P, but that is it's implied this is the case. So we say, okay, now what we do is that we say P is very far and it's very large quantity, and then we can write it as
The P is a complex number.
yeah, P is the point in the eigenvalue like, distribution, like it's just it's going.
But you can even take it to be a complex.
Yeah, of course, yeah. All of the matrix values are complex, so yeah, eigenvalues are complex. All of these-
Isn't it really worse than the Hermitian?
I mean, yeah, it is solution, but for now, we will ignore the fact that it is solution and assume that it can be any other values. I mean, of course, at the end of the day, when we write the results, I mean, it's all valid only I mean, it's, all of this is in, all of the eigenvalues will be real, because the distribution of eigenvalues will only be the real thing. But we will take some liberties when we write this because, I mean, it's not, I mean, these are something that are generally true. But yeah, the eigenvalues are real, but sometimes we say, okay, maybe they are complex, but it's not. The eigenvalues are always real. So yeah, we can. Yeah, we can write something like this. And so We can also, they can also have some other quantity called genus, which are defined later. And we can say if I have some like genus expansion for omega, it will be something like this. The uh, the term genus doesn't really do justice here, but we just say, okay, I can have some expansion like this. As long as this is mathematically valid, this is what you want, but this is, we say that there is a possibility of having genus expansion for resolvent that goes something like this. But what genus here, like, it's supposed to quantify the fact that, I mean, for now, these are just simple traits of MK. This isn't a diagram yet. But when we have these kind of things coming inside when we have products of these, when we have them inside correlators or something, then they're already correlated. So yeah, yeah. When you have products of things like this, then these genus actually take physical meaning where they are supposed to explain the geometric nature of the graph. So all these are GN0 graphs. The one I dropped, I should have dropped that. Okay. Yeah, that's the non-Gaussian graph. That's the first non-homogeneous zero graph. I don't know the exact genus of that. Yeah. So, yeah, what we do is that in planar limit, while planar is that like, there are possible, like I said, there are possible terms like this and more complicated ones that could appear. So we only take the genus zero variant, that is only the planar diagrams, and we find the writers. The way in which we can justify writing like this is these are all genus zero. I mean, like even if you have base of mk, unless you have like some square or some other terms like that, these are really all flat. So you can justify that. Another way of using to justify this is that. But we see that if we have like higher some multiple insertion, like, this is just for one p. If we can also have the resolvents defined, we can have another insertion like this here, in which case it will not be so trivial. But for now, in this case, yes, it is something that you can straight derive from the straightforward. Is that fine? Yeah, why write like this? So yeah, now that we have defined something, okay, remember this is like you might notice something similar here. This is defined like that, this is defined like this. So without the bar. So there is this theorem in math. I cannot pronounce it. So yeah, there's a theorem by these two people. Yeah, I can't pronounce it. Where you can rewrite, you can write a principal value integral in this format.
Okay, so there should actually be a principal value on these integrals?
This is the regular integral.
There's no principal value?
No principal value. I mean, from our construction, that shouldn't be a principal value. But here, we really don't know if there are misbehaviors or not. So, and that definitely possibly, that definitely will be some misbehaviors because of things like this. But here, we use the expansion to go back here. Because of that, we know we just build everything inside the integral. So the principal value doesn't appear here. So we can write this as like, if you have some principal value, you can go. Yes, we can write something like this. So what we have essentially done is we have found a way to relate the resolvent, the potential, and the density function. In this one.
You should probably take away this. Well, I don't know, it's a challenge.
Yeah.
Or maybe you might want to write these.
Oh, okay, so yeah, so it is. Yeah. So now what we want to do is that, okay, we want to use this resolver so that we are defined and try to solve the system here. Well, that's not bad, okay, but I'm more like I'm going for running for such. In Slack, right? Yeah, can you just keep it in mind, not on such. So, yeah, we have, from this equation and everything, we can write these things in terms of we can now write this. Yeah. So, yeah, now we have to, yeah. Now I'll have, so for now, we have assumed that the eigenvalues can exist anywhere, but here we have to make one specific condition. We say the eigenvalue lies only between specific given single interval, and that's all there, that's it. So it is possible that the eigenvalues can lie elsewhere, but the problem comes from the fact that if you have multiple boundaries, it's not very easy to define. But we will have real life situation where the eigenvalues can lie in multiple systems. Okay, for example, going forward, we assume that eigenvalues will lie between some A and B. This is called a single cut solution in matrix form. It could be possible that the eigenvalues will be in multiple other cuts, but for now we will focus on this. I'll slightly gloss over that. Yeah, for the case that we are interested in is J gravity, and in J gravity, we only look at a specific form of a single cut matrix model.
Should it be a class?
Yeah, sorry. Yeah, so it's in class, yeah. Yeah, so in J gravity, we look at single cut. But like recently I saw if you have DT bar deformation for matrix model, you have a system like and introduce DT bar flow to it, you will have double cut solutions for that. And yeah, that's like the only case that I've seen that where double cut actually are used, but at least double cut are used. But yeah, in most cases that we'll be interested in, it will be a single cut solution. So yeah. Now, what we can do is that we can write something like this. shit, all that. I'll explain what I'm doing, but for some again. Alright, I'll give you. So what I've done is I've taken the definition of omega zero. There. And like what I've done here, yeah, so what I've done is, okay, so I'm trying to evaluate omega zero as some, yeah, at some specific point, say P, and then as this as residue at that point, with omega naught by P minus A to P minus D as I'm trying to evaluate as a residue at some point P. Then what I'll do is that I'll use this relation and I'll also blow up the contour so that it will pick up the branch cuts that are coming from the boundaries of the boundaries in which the eigenvalue is actually lying. And then I can actually rewrite omega zero in this format. Fine. So yeah, what we do is that after that, I can say, okay, so we have P minus Z here, and we can, and since P minus, we initially started by saying that P is large and very far away from M. So because the eigenvalues of M, and Z here is in the contour around the region in which the eigenvalues lie. So you can actually expand this as the one by P into like 1 by 1 minus Z by P, and then rewrite this as yeah, what's the advantage? Yeah. That's fine. So 1 by P that you take outside of this go interior and take out of it. Yeah, this is the case. So, but yeah, so the thing is that when we took something like that to resolve, to write the resolvent, what we have implicitly assumed is that omega naught goes as 1 by P for like in case of the large P's, omega naught should actually go by 1 by P. Like for now, until this point, I haven't utilized the fact that P is very, very large anywhere. But when I use that, I should, based on that integral, I should also get that omega naught goes 1 by P for very large values. So just like, so based on that, that's clear, right? So I should have mentioned that before I forgot. So yeah, omega naught, the large of P, omega naught of P should go as 1 by P. So when you have something like this here, this integral with this one will go to 0, and all the higher leading models will also, like, we will not look at that, but this, what do you think, Nash? This. Uh, that is, this part goes to 0. And the second, this one should go as 1.
Didn't you say it should go as 1/p?
Yeah, 1 over, it should go as 1 over p here.
Yeah.
So, like, if I take the p outside,
Oh,
yeah, p outside is this. This totally goes there. So, yeah, so it should, yeah, so what we have, so when we started this, we went with the assumption that we know what, like, W of Z is, because like, that is the theory. And we assume that the matrix, the eigenvalues lies inside a specific, specific, like, curve that has boundaries defined by A and B in real life. But what we didn't know was A and B, and what we also, like, what we wanted to know was density distribution, because essentially that shows you how the eigenvalues are distributed, and that is the solution. So right now we have two equations and two variables. So with that we can actually solve single cut matrix models. Yeah. We can also rewrite this as. Sorry, you're solving for A and B. Yeah, because everything else we already know. This is something we know. What we want to find out is this, but we don't know what this is. So in order to find out this, we need to know what the boundary. We need to solve this part. For that, we need A and B. Yeah. So yeah. We can also write this. Where M of P is given by
We should never use W and omega in the same thing.
W and
And omega in the same.
I know, but yeah, the problem with how much time? Yeah. So, yeah, the problem comes from when I go to loop equations where like some forms of resolvent are also defined by W. Yeah. My vendors have decided that this is the correct way, so I can't do it. Yeah, so what happens here is that yeah, what we have done essentially is that the Z actually has two poles, one at P, the other is at infinity. So we have instead rewritten it as 1 by Z, and then try to do the same thing with the pole around the origin. And if we do something like that, we end up with something like this. So, I mean, yeah, the point for doing this is that this is not the only way to solve, but if we want to, if we, okay, so now we have solved this, but this equation is much nicer and it has another sneakier property that will learn if we do something. When we go along further, we notice that this equation actually has a much better property in which that you start really able to write higher powers of omega in terms of omega itself, where instead of MOT you have the functions of omega. And instead of this, you have higher genus or higher insertions. So yeah, so this is a precursor to what is to come. So if yeah. Yeah, another thing we can do is that we can multiply both sides by 1 by p minus lambda I. First one, lambda I, and then we sum over indices, use 1 by n, take an integral. What we essentially have is, okay, if you do that here, we just get omega naught here, we already have omega naught here, we just have another omega naught coming from this. This will give you an omega naught times W prime, and this will give you something slightly more complicated. But slightly more complicated, but easy to see. So if it's clearly so, I do something like that, to use P some. You get an equation like this. I mean, this what it essentially does is you just introduce another set of omega naught and try to rewrite it so that you try to remove integrals like this. Yeah, so this what R is. I mean, essentially what we have done is just we added this and then we just rearrange this this integral so that one will give you this kind of term, the other you can just take inside of this, and then if you solve here you have control over 0, so instead of inverse you just go back to WZ again, and then rewrite you have one term from here, one term from here. You can if you do one of the integrals, the Z1 integral, the Z integral, you will get a term like this. So yeah, I mentioned multiplicative integrals before. So here I'll try to briefly tell you why there are problems with that. Is that okay? So you have these two solutions, but instead of z minus a or z minus b, you have z minus a, z minus b, so on and so forth for all boundaries that are actually present. But what happens is you will again end up with only two sets of equations. But instead of this, you have z power n, because when you pull that out, you have only one p here. But if you have two boundaries, you have z power p power 2n. So you have z power n term here will give you 2p. But what it essentially means is that you have you again end up with just two equations, but you will have you will have you have two equations, or you only have two solutions. what do you do? One way of solving that people generally do is that you take the potential that W here and all intervals between cards. So if you have something like, you take these to be equipotential zones, and that is one way to get it the correct number of solution. And why that is correct is that, like, as I mentioned before, you have two cards in TT bar. So what happens is, I'm not fully aware of what goes on there, but the sketch of what happens is, you have like two branches of solutions, one for perturbating, the other for non-perturbating. And for a critical value of the flow equation, those two branches merge, and if you want them to merge, they have a valuable potential. Otherwise, you have all sorts of problems when you try to do that. But yeah, so generally, you take these kind of assumptions are not invalid. But yeah, so that's the only case I have known that has more than a single card, but there they have a valid reason. But generally, people say that in literature, the way in which you solve is you take two solvers to be having same potential.
So A, you don't know, you are trying to solve for them.
Yeah. So
Beforehand, if you start with some matrix model, how do you know how many of these branches will there be? How many equations will get? You don't know that, so
you don't know.
so you just start by 2 and you see it's not enough and then you add, or?
So yeah, generally what people do is like matrix model or not isn't something that's like inherently interesting. I mean, sure, it has a lot of good properties, but like, this is zero dimensional QFT. This means nothing. So people usually try to find out a dual with it, and what they do is, okay, I want okay, I'm jumping ahead, but I do not have time, so I'll probably stop here before I move on. Yeah, I think this is a good place to stop. Yeah, so stop here anyway. So yeah, what I'll give you just what this to come. So what people do is that they want to find out resolvent. Like this is the most simplest form of resolvent you can have. You can have multiple genus and you can have multiple piece insertions, and those are the ones that are actually more interesting because those are in genetic gravity cases, the multiple genus is just the connections. So those are the terms that are more interesting. So when you want, when you, but in those cases, you already know what kind of resolvent you're looking for. So when based on the resolvent, you can you're trying to set out, you can try to set the potential and the boundary conditions so that you can you try to manipulate whatever is inside here to get the desired form of resolvent. You really do not, for example, in case of genetic gravity, I mean, I haven't actually seen the potential. As long as you know that this is well behaved, you don't really care about it. All you care about is this. Because what you can do is something like this is just a precursor of what is to come. In this case, it's just like 2 omega naught square or something like that. You can go further, and what you can do is that like if you you can do something called the loop insertion operator, and what that is that it just keep bringing down. Yeah, I erase that. Yeah, I erase that anyway. So you keep bringing down the m square or a power n terms from matrix model. You take a generic matrix model and all sorts of possible terms. You just keep bringing that down, and then you try to construct like a series of like you take a derivative inside, and that should be zero because it's particle inside particles and all that. There's no boundary, so you take that. You say, okay, what does this equation give you? What the equation gives you? So yeah, most probably zero. So what the equation gives you is a way to take lower order resolvents to higher order ones. So what you do is that, okay, omega zero is something, in most cases, but in case of data, I mean, this is a classical solution. So once you know that, and once you're able to find out the very small information, you don't have to really yeah, so if you see the experiment, if I have a next session, I'll try to go in depth. So what you do is in JDR, you have something called Bell-Peterson model of form. So people are able to show that that volume will be you can do an integral transformation and get the resolvent type of equation, and people have proved that you can have form a matrix model for which this resolvent is just an integral transformation of the volume inside. But the volume is not very easy to calculate because it's a very complicated thing. So what you do is that once you establish duality, you just say, okay, I know the lower order one, so I know how to input the value for this. And then I know matrix models are something called loop equations, so I just go ahead and then solve order by order, in which case you can have the changes to multiple insertion corrections, or you don't have to do anything, you just have to recursively solve for that. So yeah, that is why I mean, I know like matrix model is something good, but people generally do not care about these things because these are just hindrances for you to find out what omega means, what the result is. Ultimately, that's all you want. In case of baby data, the dual is something called double scale version where one is at the origin, the other is at infinity, and you don't scale by n like here. You scale by something, you scale by exponential of entropy because the J gravity has the first is if you have quantity function, the first quantity is the e power of chi, so f not chi. So and then you have another term that says R2. So yeah, you are there. And the point is that these are just tools. So for now, it is true that that there are many more interesting ways in which this is solved, but for physicists, it's not really it's not too interesting. There is this book by Madhavan Mehta for mathematical issues, and then there's a book for random analysis, for especially physics. It's like Marcus Marino. Yeah, that goes into depth. Whatever we need for physics case, but yeah, if you there are no cases to, yeah, I'll stop here. So yeah, thank you. Questions?
Yeah, so can you just tell us some applications of this, except for the GT gravity, or is it mostly used in GT?
Like Sarchek also showed that there's a version of something called linear strings in which I don't remember the way back from I didn't know street, I have very knowledge of string is scanning. They have something called some disconnected G0 planes, only sheet action could be replicated from modification of matrix models. So, and yeah, Witten showed that you can have normal steady gravity is straightforward, is at R2 and so on. You can have some fluctuating, you can turn on some other fluctuation in bulk as well. And we have some dual potential and try to find out the duals. And I mean, yeah, there are a lot of matrix models with stuff, but most people are focused on JDRD because it's most, like you saw, you ordinarily have that Maxwellian repulsion for a two-dimensional formula. So, and the indices are mostly this two. So, I mean, and it's not that you cannot do it, but for now, yeah, people are sticking to two-dimensional because there's an easy way to establish a rule.
Thank you, speaker, once again. There's no more questions. Yeah, we can arrange for another talk sometime if you want.
Yeah.
Maybe after Christmas.
Yeah, sure. Yeah, we